right, so at the end of last week, we looked at, well, kind of in the middle, we looked at starting trig, okay, which looks at converting between degrees and radians. I think we did a little bit with arc length, angular velocity, and that's all very numeric and using a formula. This week is going to be more graphical. Okay, so we're going to look at what does it look like when we actually sketch out some of the functions that we're going to be working with quite a bit. Okay, we're going to start by looking at the sketches of sine and cosine. Now, all the trig functions, sine, cosine, secant, cosecant, tangent, and cotangent, they're all what we call periodic functions. So the idea of a periodic function is that it repeats itself. It's like once you draw one section of it, you could just copy and paste that section forever and see what the graph would look like. No other graphs we've studied this year do that, really. They don't repeat themselves in the exact same pattern over and over again. Okay, and I'll show you an example of what that looks like. And also explain what this last part means, where it says over a given set of x values. I think a picture will help that. All right, so let me show you on the calculator first what the graph of sine looks like. One thing we're going to do a little bit different here is the window. So there is a special window that we use on the graphing calculator when we're looking at the graph of a trig function. I don't really think you need to try this. You can just watch it. You just press zoom 7. So if you do zoom 7, that says it's a trig window. So it's a window that's really designed to make a trig function look good. Right? So there's a graph of the sine function. Right, so sine and cosine both have a look pretty similar to that. Kind of have this wave pattern to them. And if we look at one section of it, that one section basically predicts what the whole thing is going to look like. So let's look between that red line and that red line. So in between those two red lines, we could consider that one section of our graph. And there's a better name than section, and I'll tell you what that is in a little bit. If I take what's between those two red lines and I copy and paste it, just like put it right there, then I get another section of the graph. And I could copy and paste it again and get the next section. So this graph is going to continue forever, left and right, repeating the pattern that's between those two red lines. Now, I said that let me go back, that the y values will repeat over a given set of x values. This, from here to here, that's the width of the x values that you have to go through at least once before you can then take that and repeat it. Like if you stopped here and you said, oh, is it just this repeating over and over? So it just, it looks like this? No, that's not the part that's repeating over and over. Okay. To get the full part that's going to repeat over and over, you have to start at the red line on the left, and you have to end at the red line on the right. Okay. That's the width of the x values that you have to go through. And if you look at the y values, they start at 0, they go up to 1, 0, -1, 0. And that's the pattern that keeps repeating. 1, 0, -1, 0. Those four numbers keep repeating. And those give you what we call the four most important points in the graph. Okay, they kind of give you the start, the highest, the middle, the lowest, and then that's the end, which is really the start of the next one. Okay, so that 1, 0, -1, 0. We keep seeing that pattern repeat. Okay, any question on that idea? Okay. So the length of that interval that you have to go through, like between those two red lines, That's what one full section of the graph looks like. Okay, that's called the period of the graph. It's the length of the interval that you have to go through before the graph will start to repeat itself. And for sine and cosine, the regular period, if you don't stretch it or shrink it or do anything to it, is 2 pi. 2 pi radians. So just to be clear about what you're graphing, okay, what the x-axis and what the y-axis represents. The x-axis represents an angle. Okay, that's what the x-axis is. It's an angle. The y-axis is, in this particular case, the sine of the angle. Okay, so the x-axis is an angle, and the y-axis is the sine of the angle. And the way when we do the Zoom 7, it sets up everything nice so that we have 4 tick marks in each cycle. So we start at 0, and the first cycle ends at 2 pi. So what angle would be right in the middle of the cycle in radians? Yep, pi. If you're thinking in degrees, that would be 180. What angle would be between 0 and pi? Yep.
Pi over 2.
Pi over 2. And if you write everything with a denominator of pi over 2, you'd see a pattern. 0 pi over 2, 1 pi over 2, 2 pi over 2. This last one is 4 pi over 2. The middle one here is 3 pi over 2. Okay, those are the x values of all the tick marks in that cycle. If you're looking at it in degrees, that's 0, 90, 180, 270, 360. So 2 pi is the end of the first cycle, and it's the beginning of the next one. So if you wanted to see exactly one cycle, okay, on the calculator, you could set your window to do that. All right. So we turn the calculator on. Let's start it. All right, so this is in degrees. Let me switch over to radians. Let's set it from 0 to 2 pi. So now you're going to see exactly what's between those red lines. And you only ever need to go as high as 1 and as low as -1 if you don't stretch it or shift it, do something to it. Okay, so let's go -2 to 2. And along the x-axis, I want to put a tick mark. I like to space it so that there's 4 tick marks in each cycle, so you can easily see like the quarter points. The first quarter, second quarter, third quarter, and then the fourth quarter, which is the end. So let's put a mark every 90 degrees, and if we were doing it in degrees, well, let's do it in radians. So every pi over 2 radians. All right, so there's the halfway, there's 3/4, and there's 4/4. So now you're looking at just that one section. Now, what if I wanted to show 2 sections on the calculator? What do you think I would have to change my x max to see 2 complete cycles? So basically what I have in red right there. Yep. Maybe
4 pi.
4 pi. Okay, if you went all the way to 4 pi, well, we know that one cycle has a length of 2 pi. So if your window has a width of 4 pi, you're going to see 2 full cycles. Right? And they may ask you to set your calculator to a window so that you see a certain amount of cycles. And that's how we do it. All right. Questions on that idea? All right, so I'm going to write down what these 5 black dots are in a little bit, those coordinates, because those are the coordinates that we use to do all the graphing for the sine function. We always start with those 5. And then we do whatever we need to. We shift them, we stretch them. We just have to look at the problem and see what it says to do. Okay, so another name for the period of a graph, it's also called the cycle. I think I might have already been using that term anyway. Cycle is used more when you talk about like electronics. If anybody is in engineering or maybe electrical, you talk about cycles too, like electricity. Electricity in the United States runs at 60 hertz, and hertz is an abbreviation for cycles per second. So it's measuring, if you look at a picture of electricity, which you can do, right? If you have a multimeter that's fancy enough, you can actually see the way the electricity looks for alternating current, and it looks like a wave pattern. Not the kind of electricity in your car, that's a battery, that's direct current, so that's different. But the kind of current like, in a building that you plug something into. So one thing we can take a look at is, from transformations, you guys should know what these are going to do. What does a negative do when you put it either in front or on the inside? It causes a what? Yep.
A flip.
Causes a flip or a reflection. The first one is a horizontal reflection. The second one is a vertical. Well, let's see what happens if we take sine and reflect it horizontally, and then take sine and reflect it vertically. And let's watch what happens. So there's a reflection of sine horizontally. And if you compare that to reflecting sine vertically, how do they look? Kim?
They're the exact same.
Yeah, they're the exact same thing. That's why I wrote up there they're equal. Okay, I'm just showing it to you visually rather than writing it as an equation. So what that means is if you can flip something horizontally and it's exactly the same as flipping it vertically, the name for that is symmetry about the origin. So the sine function is symmetric about the origin. Because flipping it horizontally and flipping it vertically does the same thing. Question?
Is there any way to make it so it's not symmetric about the origin?
If you shifted it, then yeah, that might not work. So let's say you took, let's see, we're in radians, so let's shift it, and you guys should probably already know what this is doing. We're going to shift it 1 unit to the left. All right, so right before we stopped, there was a question about whether or not you could make it so that they're not symmetrical. What I did is I put in a +1, which is going to shift it 1 unit to the, let's see, +1 would shift it left. And if you do that, then they're not lined up anymore. Usually when we talk about a function and different properties of it, we're just looking at like the base case of the function, not if you shifted the function and then did something. All right, but the basic sine function does have symmetry over the origin. Now, if we look at cosine, and this formula is going to come back to help us out a couple times, because what this basically does is it gives us a way to get rid of a negative inside the argument. It turns out that if you're dealing with cosine, you don't even need the negative. If you have a negative inside, you can just get rid of it, and it doesn't matter. With sine, you can't get rid of it, but what you can do is move it to the front. That's what this formula is showing you. All right, so let's take a look at cosine with a horizontal reflection. So cosine of -x and cosine x. So this will be our first time looking at cosine. But you see it still has a wave pattern to it. If you're not sure how it's different from sine, I'll graph the two of them together in a second. But what I'm trying to show you here is that cosine of -x and the cosine of x are the same thing. No difference. Now, let me graph sine and cosine on the same window. Let me do a zoom 7 because that'll just zoom us out a little bit. All right, so that one is sine. I can tell by something about it. And that one is cosine. So they're very similar. They're basically horizontal shifts of each other. Okay. But when we start looking at the tangent and the secant, and those look very different. Okay, but sine and cosine look pretty similar. So cosine doesn't have symmetry about the origin, but it does have symmetry over the y-axis. You can do a horizontal reflection, and it looks the same as the original. So when we're graphing sine and cosine, we really need to pick 5 points to make a graph. And I tried to show you guys those points earlier right here. They're those 5 black dots. Okay, those are the 5 points that we usually use when we're trying to make a sketch. Gives us the beginning and the end, the middle, the highest, and the lowest. And they're the quarter points of the function, of the cycle. All right, so here's the same sketch again. So these 5 points are all pi over 2 radians apart. That puts them at the beginning, first quarter, second quarter, the third quarter, and then the fourth quarter, all the way. If you wanted, you can do more points, but generally when you're graphing sine, if you've got those 5 and then you connect them with a smooth curve, that's plenty of points to graph. Okay, one thing we don't want to do when we're sketching sine or cosine is sketch it like that. Okay, nothing about the graphs of any of the trig functions are linear. They all have curvature to them. Okay, specifically, I don't want to get into it too much, but when you take calculus, you talk about concavity. And if I draw this graph, from here to here, this section is what we call concave down. It's concave down. This section is concave up. You can think of a concave up graph as it would hold water. Like if you poured water into it, it would stay in that section. That's concave up. This is called an inflection point. It's the point in a graph where the concavity changes from going concave down to concave up. Again, we're not going to study too much about those terms I just said, but if you think of that when you're sketching it, it should remind you that part of the graph curves down in the cycle, and the other part curves up. Okay, that's called concavity. So anytime we want to graph a transformation of sine or cosine, what you're always going to be graphing is, let me do what's in black. I'm always going to have you take that one cycle and do something to it. Because my assumption is if you can sketch one cycle of the graph, then you could sketch 2. Just copying and pasting what you do for the first one. So all you're going to have to do when you do a transformation is take this one cycle in black and do something to it. Okay, maybe you'll do a shift up or shift down, or you'll shift it left or you'll shift it right, or we'll also talk about stretching. Okay, but you're only going to have to sketch that one cycle transformed. So because we're only sketching that one cycle, you're always going to start with the 5 points that represent that one cycle. These points are these points right here. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi 0. Those are all the numbers that I just read in that table. So, on the left, the x value is an angle. So this represents an angle. Specifically, we're using all the angles at the quarter points to get a nice graph. And this, well, you can read it right up above. Y represents taking the sine of the angle. Okay, the y-axis is always the angle after you take the trig function. So if you ever forgot, you could just type them in and see what they come out to. But if you put in 0 for sine, you get 0. That's the first one. If you do the sine of pi divided by 2, that's how we get 1. That's the second one. Okay, so the y column is after you take the trig function of the angle from the x column. Now, let's go back and let's look at cosine. Okay, cosine is in red. If you look at cosine, these are going to be your 5 points. 1, 2, 3, 4, and 5. So it gives us a different part of the wave. It's still the wave, but it gives us more of the V-shape part of the wave, the concave up part of the whole thing. So rather than having half that's concave down and half that's concave up, we have a full concave down section. But we're generally sketching the first positive cycle for the graph. That's what I have you do. Okay. So for cosine, it just happens to look more like a V shape. Not a V where it comes to a point though. Make sure it has a curve to it. So we're going to have the points 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, we're back at 0, and 2 pi, we're back where we started at 1. So those are going to be all the points in that table. So the x values are the same in both tables, but the y values are different. So we have to make sure whatever graph we're doing, that you're using the right table. If you're doing a problem about sine, table on the left. Problem about cosine, table on the right. And if you ever had to sketch more than one cycle, just extend the pattern you see in the table. Here's the pattern of what you're really seeing in this table. That's 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. So if I wanted another x value right here, what would be my next x value? Yeah?
5 pi over 2.
Yeah. If I was going to graph more points, I could do 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. Of course, some of those reduce. So extend the pattern in the x column, and then extend the pattern in the y column. 1, 0, negative 1, 0, 1. 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 You can just keep listing those numbers down, and you get another cycle of the graph. And same thing here. Just continue the pattern for the x's and the y's, and you can continue the pattern in each direction. This would continue the pattern to the right. I could also be subtracting and do like negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4 pi over 2. I could continue the pattern in each direction. Okay, but any question on those two tables? So we're going to start out by doing individual transformations. Again, I kind of explained this from the perspective that people haven't seen transformations before, but you've seen them many times. If you only do one transformation to the points in the table, like let's say you shift left. Well, if you shifted left, which column here would be affected by that? The x column or the y column? Okay.
X.
Yeah, the x column would be affected. The y column would not change at all. If you move something left, it doesn't change its height. All right? So when we do a single transformation, which is what the first two parts of this lesson look at, all you're going to do is have to change the values in one column. So one column will stay the same, the other column will change. In the third part, which we're definitely not doing today, The third part gets into multi-step transformations. The only thing that's different there is a certain order you have to follow. What's the order? The same order you followed all year with A, B, C, and D, okay, when you do transformations. So the first transformation we're going to talk about, and I kind of break it down into talking about each transformation one step at a time. So if you've had trouble with transformations, hopefully this will be nice and slow. So the first one is a phase shift. Okay, phase shift is just a fancy name for a horizontal shift. I'm not sure why with a trig function they call it a phase shift. With every other kind of function, we just call it a horizontal shift. And when you describe it, you could still just say shift left or shift right, 5 units, 6 units, whatever it is. But the shift amount is an angle. So a lot of times when we shift, we pick an angle that's a nice number to shift by. You're probably not going to shift left by 7.6 degrees. That's kind of a weird amount to shift by. Common amounts that you might see, a 30-degree shift, 60 degrees, 45 degree, 180 degree. Okay, numbers like that are usually what we shift by. Okay, nice values, multiples of 30 or 45. So phase shift or horizontal shift, it's just when your graph is translated left or right. And that's the form of a phase shift. It involves addition or subtraction inside the parentheses. Now for either one of them, if I do addition, which way does that shift the graph? Addition would move it to the left, and subtraction to the right. Good. And again, I'm really breaking it down here. Right? So if the argument is a minus, that's going to shift it to the right A units. Remember, you never shift by a negative amount. That doesn't make sense. Your shift is always left or right, and the number you put in front of that is positive. Right? Shift left 5 units. Shift right 5 units. Okay. If the argument is x plus a number, plus is going to shift to the left. Okay, so all stuff we've seen before. The only thing that's a little annoying about shifting left and right is that affects the x column. And your x's have all those fractions with pi. 0, pi over 2, pi, 3 pi over 2, 2 pi. We never use decimals. Okay? No decimals will ever be used if you have a number with pi. You have to keep it exact. So that means we're going to be working with fractions, and we may have to add or subtract numbers to fractions. Okay, so we need common denominators. But that's really the worst part of a phase shift. All right, so when you are doing a phase shift, you're going to start with the original table. Okay, I gave you an original table for sine, and then I gave you a different one for cosine. Well, phase shift is horizontal. Horizontal has nothing to do with the y values. So when you're doing a horizontal shift, copy the y values down from the original table. Those don't change. And the way I would grade a problem like this on a test is on the test in Edulastic, you're going to see a table like this. It will be blank. There'll be 5 blanks for the x's, 5 blanks for the y's, and you'll get 1 point for each number that you get right in the table. So the table would be worth 10 points on the test. In a problem like a phase shift, if you don't get the y's right, it must mean you just copied them down wrong, because there is no calculation for the y values in a phase shift. Just copy down whatever they were originally. They don't change. But to find the new x's, first we're going to look at what's been added or subtracted from our argument. So like the first one we're going to do, we've subtracted a pi over 2. And can someone remind me, subtraction moves the graph which way? Yeah?
Right.
To the right. And what happens to your y values? Oh, I'm sorry, what happens to your x values as you head to the right? Because all these x values are going to move right. They should get
bigger.
They get bigger. So what that means is whatever you see here, they're going to get bigger by pi over 2, because they're all going to move to the right. So we're going to add pi over 2 to shift them all to the right. If you subtracted from the x values, you would actually be moving them to the left. We don't want the x values to get smaller. Okay, when we see a minus, we know that it shifts right. If things are moving to the right, they need to be getting bigger. That's how you shift things to the right. So look at what's been added or subtracted. In this case, it's a minus pi over 2. We know minus means shifted to the right. So how do you move things to the right? You make them bigger. How much bigger? Well, you just have to look at the problem and see how much that they shifted it by. In our case, it's going to be pi over 2, which is a 90-degree shift to the right. So that'll be the first one we'll do. First, we'll come up with the table, and then once we have the table, we'll make a sketch. Now, if you print out the worksheet for homework, it's set up exactly like the test is set up. You have a grid already drawn for you. If you don't want to print it out, you can do it just like I'm going to do on the whiteboard. I'm just going to draw my grid by hand. That's all. All right. So let's make our table. The table is going to have 5 points. A lot of times we use the table on the calculator to get the points. The problem with using the calculator here is it's going to give you decimals. I don't want decimals for the x values. I want all fractions with pi. Okay. All right, so let's put the original y values for sine. Okay, so what I usually do is, after a while, you start to remember which one is sine and which one is cosine. That's what sine looks like. So can somebody give me my y values, either by looking at that graph or just go back in your notes and look at the table? Yep.
0, 1, 0.
Yep. So 5 points right there for those y values. Now, off to the side, I like to put the original x values. I'll put the final answers in that box. Fix that. Okay. Okay, what are my original x values for either sine or cosine? I'm looking for those original quarter points. Yep.
0, pi over 2, pi over 2, pi.
Yep, so those are just 5 nicely spaced x values that give you the beginning, the end, the middle, the high, and the low. Now, we're going to shift those points to the right. So you just said if we shift to the right, these all need to be getting bigger. So we're going to add something to all of them. How much bigger are all these x values going to get? Yep, Caleb?
By pi over 2.
By pi over 2. All right. So the first one, that's easy. 0 plus pi over 2 is pi over 2. Second one already has a common denominator. What's 1 pi over 2 plus another 1 pi over 2? Yep.
2 pi over.
That's 2 pi over 2. And I'm going to leave that there so you can see a pattern, but I am going to reduce it for the final answer. If I reduce it, you won't see the pattern as nicely, but that's why I'm going to leave it like that. Okay, next one, we don't have a common denominator. What's the denominator on pi right now? 1. So the common denominator would be 2. So we're going to multiply top and bottom by 2. What's 2 pi over 2 plus 1 pi over 2? Yep.
3 pi over 2.
So that's 3 pi over 2. Next one already has a common denominator. That's 4 pi over 2. But again, that reduces to 2 pi. And let's do the last one. What's my common denominator there? 2. So multiply top and bottom by 2. What's 4 pi over 2 plus 1 pi over 2? 5 pi over 2. Now, if you read everything with a denominator of 2, you will notice a nice pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. The next one would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. Okay, so there's your table. Any questions on that? All right, and to make my sketch, I just drew coordinate axes. I don't need to go any higher than 1 or lower than -1 on the y's. So I really don't even need to label the tick marks if you're going by 1s. I'm going to go by 1s on the y, but on the x's, I'm not going by 1s. So I do need to label them. Remember, these are all equally spaced. This is 90, 180, 270, 360, 450. If you want to think of it in degrees, it's just plus 90 each time. That's the only condition you need to meet when you want to label tick marks. You have to use numbers that are equally spaced. You can't use something like this. You can go by 1s, you can go by 3s, but you can't go by both at the same time. Okay? So let's use our x values because we know they're equally spaced. I'm going to put 0, I don't need it, but you can't label the axis anything other than 0. It has to be 0. And the next one is pi over 2, pi, 3 pi over 2, 2 pi. I put my labels a little bit lower because when I do my sketch, I don't want to draw through my labels. All right, so pi over 2, 0, 1, 0, -1, 0. 1, 0, -1, back to 0. And there's my sketch. So that's the new graph, okay, or the one that the transformation was applied to. The original would have not been shifted to the left, and it would have looked more like that. So on some problems, I may have you do a sketch of the original, so you can show me where that was, and then do a sketch of the new one. You can do one in pen, one in pencil, or just label them, as long as you know which one is which. Okay, so that's a horizontal shift, also called a phase shift. Any question on that? All right, let's try, let's see, let's do this one. All right, so first of all, once we know more transformations, we have to identify what that one is. What does adding inside parentheses always do?
Move it left.
Yep, it always moves it to the left. So the y values are not affected at all. What are the y values for the first cycle of cosine? Yep, Mabel?
1, 0, -1, 0.
Okay, so there's my y values. Put my answers in that box. I'm going to put my original x's off to the side. And now we're moving it to the left because that's plus pi. How much are all these points moving to the left? How much? Yep.
180 degrees.
180 degrees or pi. And if things are moving to the left, what happens to a number as it moves left? It decreases. How much? All right, so we're going to get negative pi over 2, 0, pi over 2, and pi. Any questions on how I got those? I did all common denominators, but I just kind of did it in my head as I went. And the ones that are just like the first, the third, and the fifth, those are a little easier because you don't need common denominators. Pi minus pi is 0. 2 pi take away 1 pi is just 1 pi. Any questions on those x values? All right, and now we just make a sketch. Okay, again, everything here is equally spaced by 90 degrees. Negative 180, negative 90, 0, 90, 180. So this time you're going to need a couple tick marks on the negative part of the x-axis. So negative pi, pi over 2, negative pi over 2, 0, pi over 2, 5. Okay. 1, 0, negative 1, 0, 1. So 1, 0, negative 1, 0, back to 1. Now it does look kind of like a V shape, but remember this graph is a curve. So it's really that part of the graph. Okay, so try to make sure it has that concave up look to it. Yeah. Okay, so that's been shifted to the left. The original graph would have started with this point over there. Okay, I'm not going to sketch the original this time, but any questions on that one? Okay. Let's look at this one, basically because when you set up your labels on the x-axis, you have to be a little careful. All right, what are going to be my y values here? Yep, John?
This should be 0, 1, 0, negative 1, 0.
Okay, so no change to the original y values in the first cycle. But we're going to take all the x values, which, Madison, can you tell me what my x values are?
0, pi over 2, pi, 3 pi over 2, 2 pi.
Okay. And what am I going to do to all of those? Nick?
Subtract pi over 4.
Yep, we're going to subtract pi over 4. Now, this is one, I'm not going to find the common denominator every time. I'll do it for the first 2 or 3, and then I'm just going to see if I notice a pattern. All right. Annalise, what's my first one going to be?
Negative pi over 4.
Negative pi over 4. Now, common denominator between a 2 and a 4 is how much?
4.
4. So double the bottom, double the top. What's 2 pi over 4? Take away 1 pi over 4. Caleb?
Pi over 4.
Pi over 4. Let's do it again here. Common denominator between 1 and 4 is 4. So multiply the bottom by 4, top by 4. And what do I get for my x value here? Yeah. 3 pi over 4. So now if you look at the pattern of the number in front of the pi, negative 1, 1, 3. What's the next one going to be? John?
This one. That's 5 pi over 4.
That's going to be a 5 pi over 4. And what about the last one? 7 pi over 4. If you don't see that pattern, you can go ahead and do the common denominators, but that's what you'll get. Okay, questions on that? Now, let's think about setting up the, actually, I already have it drawn. Yeah. Let's think about setting up the labels on my x-axis. Now, let's just think about it even simpler at first. Just look at the numbers in front of pi. Negative 1, 1, 3, 5, 7. Okay, let's put those numbers on the number line. Where would negative 1 go? If you were putting that on the number line. Yep.
Somewhere before 0.
Before, can you tell me exactly where?
Like the first one before 0.
Before 0. So there's negative 1. Now, where would 1 go?
The first tick after 0.
The first tick mark after 0. Now, where would 3 go? the third tick mark, not the second tick mark. Okay, and then 5 would also skip, and 7 would skip. These are going to skip the same way for the same exact reason. We're not really using 0. 0 is just there because it's what the y-axis always is, 0. But really, you're skipping every other tick mark with the way these labels are set up. So the first one is negative pi over 4, which is 1 tick mark to the right. The next one is pi over 4, 1 tick mark to the left. And you really skipped right over the axis. You have no label there. So if you skipped a tick mark one time, you have to skip it every time. So then this would be 2 pi over 4. This one is 3 pi over 4. 4 pi over 4, not using. 5 pi over 4. 6 pi over 4, not using. 7 pi over 4. And that's the only thing that's tricky about that one, is setting up your labels. Right, 0, 1, 0, negative 1, 0. 0, 1, skip, 0, skip, negative 1, skip, back to 0. You'll also know if your graph is wrong, especially if you use graph paper, because if you get something that looks like this, where like the first part of your graph is really squished and then the second part is really stretched out, then you know this point probably shouldn't be there. Maybe it should have been over here. So your graph looked more like that. So if you draw it with graph paper, those kind of mistakes become pretty obvious. All right, so any question on doing a phase shift? All right, so I think we'll take a look at just one other one today, which is the vertical shift. So we're going to do both the shifts today. We'll do the stretches tomorrow, and if we get through those really fast, then maybe we'll do 6.3 part 3 with 6.3 part 2. But I think 6.3 part 1 for today is probably a good stopping. Okay, can someone remind me from other transformations we've looked at, how do you know if you are vertically shifting a transformation? Tell me what operation it is and where you would see it. Yep.
Plus or minus outside the function.
Right, this is the plus or the minus outside the function. So you're not adding the plus or the minus to the argument and then taking the cosine of something you've added or subtracted a number to. It's like you're doing this. You're going to take the cosine of an angle, and then after you do that, you're going to shift it up or down d units. And again, I use d because if we were doing all 4, that would be the last one you would do, vertical shift. Which way is up? Yeah? Plus, and minus is down. So I added in these parentheses. You don't need those there. If you had something like this, when you think about order of operations, trig functions always take precedence over adding and subtracting. So if this was like cosine of, let's say, 30 degrees plus 3, you always take the cosine of 30 first and then add the 3. Trig functions have a higher precedence than adding, subtracting, multiplying, or dividing. So this or that mean exactly the same thing. Okay, so what you're adding or subtracting is outside the argument. This time, remember when we do vertical transformations, what you see is what you do. You don't do the opposite. Add is up, subtract is down. So we are moving up and down. So when we think about our table, which column is going to be affected this time? X values or Y values? Y's. Okay, so this time the X's stay the same, and it's always nice when the X's stay the same because now we don't have to work with those fractions with pi. So for today, every problem with a vertical shift will have x values of 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, that won't be true tomorrow or Wednesday when we start doing multiple transformations, but for today, if we're shifting it up and down, we're not going to do anything else. That's all we're going to do. All you have to do to find the new y values, if you're shifting up, you're going to add whatever the shift amount is to the original values. If you're shifting down, you're going to subtract the shift amount from the original y values. And remember, the y values are just zeros, ones, and negative ones. Very easy to add and subtract numbers to a 0, a 1, or a negative 1. So out of the two transformations we're doing today, this is much easier with the arithmetic. So let's try this one. Cosine of x plus 2. Now we know two transformations. First step is to figure out which one this is. Okay, what kind of transformation is this? Phase shift? Vertical shift? Yeah.
Vertical.
Vertical. How do you know?
Because the plus is outside.
Right. Plus 2 is going to get applied based on order of operations after you take the cosine of x. So that's going to be a vertical shift. All right, Sophie, what values here are going to be unaffected by shifting vertically? The x's. So let's keep the x's the same. Michael, can you tell me what my x values will be? Remember, they're going to stay the same, so there won't be any change in them from what they would have been in the original table.
Oh, so it would be 0, pi over 2, pi, 3 pi over 2, and then 2 pi?
Yes, very good. So 5 points just for getting those. All right, now, how about Annalise, what are my y values for cosine?
0, 1, 0. Oh no, is it 1, 0, negative 1, 0, 1?
Yes. And Nick, what am I going to do to all those y values?
Add 2.
Add 2. So Lindsay, if you add 2 to all those y values, can you tell me what you get?
3, 2, 1, 2, 3.
There we go. So there's your table. So very, very easy arithmetic. Let's set up our graph. This time my graph is going to be pretty much contained in quadrant 1, so that's the section that I kind of focused on drawing. There's my y values. There's my x's. And let's sketch. So, you know what, let me make it so I can see it all. 0, 3, pi over 2, 2, pi 1, 3 pi over 2, back to 2, and 2 pi. We're at the end of the cycle and the beginning of the next. Any questions on that? I didn't do as good of a job as I probably could have, but. All right, so that's a shift. Which one was that? That was shifting up. Let's do one where we shift down. So, Julie, can you give me my x values?
0.
Yep.
Pi over 2, pi, 3 pi over 2.
All right. And about Sophie, my original y values for sine?
Is it 1, 0? Oh, sorry, 0, 1, 0, and then 1, 0.
All right. And how about, Maddie, can you change all these y values to what they should be if we shift them down 3?
-3, -2, -3, -4,
So this graph has been shifted down, so I focused mostly on drawing quadrant 4. We can put our labels right above here because we're definitely not going to be drawing in that quadrant. And make our sketch. So -3, -2, -3, -4, and -2. It's hard for me to see, but when you have graph paper, it's easier. And there's a shift down 3 units. Any questions on that? Right, so tomorrow we'll look at the 2 other transformations that are the stretches, the horizontal and vertical stretch. If we have time, we can also do something with some sound frequencies, because if you are familiar with sound, a wave is basically what sound looks like when you look at it with an oscilloscope. So I'll see if we have some time to do some stuff with sound frequencies and cell phones, and it's kind of neat, so we'll see. Okay, so the homework tonight is a worksheet on Schoology. Those are the 7 questions that are on the worksheet. Okay, they're all phase shifts and vertical shifts. Okay, so it'll be in the video right here, and it will all be in Schoology as well.